Did you know that silver doesn't have to be silver? Bananas can be green, yellow, brown, and eventually black. The sky can transform from a melancholy red to a blue and then to a grey. But what if I told you that silver can in fact form every tinge of the rainbow? As part of the Chemistry 2016 Semester 1 project, our group under the guidance of Alex Ewan formed Rainbow Silver. Though we didn't do it by painting over the top of strips of silver or adding an Instagram-esque filter to this production. Instead, we varied the lengths of silver, producing a dichotomy of central wavelengths to the eye. We aren't talking about using industrial drills to produce meter-sized silver bars. Instead, we're far closer in the nanoscale. If you pinch your fingers together, 1 billion nanoparticles can fit between your fingers. Nanoparticles are 10 to the minus 9 meters. We can form different colors by changing the size of the particle, which changes the frequency of which the plasma surface resonance occurs. You have no idea what this means, and I have no idea what this means either. So let's follow the yellow brick road and hopefully there will be a rainbow at the end of it. When you have a lot of silver atoms clumped together, there are lots of free electrons on the surface of the metal. When a certain wavelength of light is incident on the metal, these electrons will oscillate at the same frequency as the incident light. This means that the light is absorbed, and this phenomena is called surface plasma resonance. In bulk metal, because there are so many atoms, the wavelength for which surface plasma resonance occurs is not within the visible spectrum. So all photons of visible light are reflected and the metal looks shiny. However, in a nanoparticle, there aren't a lot of silver atoms, and this means that surface plasma resonance can occur with visible light. Hence, nanoparticles can absorb certain wavelengths of visible light. The exact wavelength that is absorbed changes with the size of the nanoparticle. Wavelengths of light correspond to color. If a certain wavelength of light is absorbed, the color that we see, funnily enough, is actually the opposite of the absorbed color on a color wheel. Since different sizes of nanoparticles will absorb different wavelengths of light, this means that we can get different colors of nanoparticles by changing their sizes. So how do we make rainbow silver? We start off with a solution of silver nitrate. This contains silver ions, which are going to form our nanoparticles. We add sodium borohydride to reduce silver ions to form solid silver. But if reduction keeps on going, we're going to get bulk silver, which is shiny and doesn't give us pretty colors as we want. That's why we're going to add hydrogen peroxide to reduce silver solid back to silver ions. These two reactions form an equilibrium, so we get very small bits of solid silver, forming our nanoparticles. To make sure that our nanoparticles don't clump together to form bulk metal, we also add sodium citrate. Citrate binds to the surface of the nanoparticles, preventing other nanoparticles from attaching, resulting in the stabilization of our nanoparticle. But finally, how do we control the size of our nanoparticle? To do that, we change the amount of potassium bromide added. Bromide ions bind to the surface of silver nanoparticles to form silver bromide. Hence, more silver atoms cannot be added to the nanoparticle, and thus it cannot grow in size. Hence, the more potassium bromide we add, the smaller the nanoparticle size. By adding different amounts of potassium bromide, we've managed to get all these pretty colors. We've managed to make our rainbow silver. I hope you enjoyed today's production. Please take a look at our bloopers up next. We've had a lot of fun over the last few weeks making silver particles. From Group L, consisting of Amanda Young, Johnny Zhang, Jackie Zhang, and William Zhao, we'd like to thank Alice Williamson, Alex Yuan, and Edwin C. for leading such an amazing project. So we have Amanda putting the 2.5 mils of the thing in. So now it's turned black, as you can see.
Sorry?
like we got two cameras. We need Jackie to get his phone out too.
Jackie's off being hungover.
So go on. No, that's right, I did that out. Yes, yeah, this is the primary camera, bro.
Your long shot is too long.
This is a continuous story.
This is not Birdman.
But who does he think he is trying to